Hi class, so today we're just continuing on our conversation of discontinuities and rational functions by talking about oblique asymptotes. So the lesson won't be as long for today, but you're expected to fully understand the other three: vertical asymptotes, infinitesimal wholes, and horizontal asymptotes before we get to oblique asymptotes. Okay, so make sure you have a full understanding of the last video. So a rational function f at x equals p at x over q at x has an oblique asymptote only when the degree of p at x is greater than the degree by exactly 1. Okay, so in other words, it's top heavy, but only by 1 degree. Okay. Now, this should make sense to you because if you have, let's say, a quadratic divided by a linear, then your remainder would be what you would have left would be a linear, and that's why you get a linear asymptote. So an oblique asymptote is just a line that is an asymptote, but it's just that it's not vertical or horizontal; it's on a slant. Okay, so notice that this will have an oblique asymptote because the numerator has a degree of 2 and the denominator has a degree of 1. So those are exactly 1 apart. So therefore there's an oblique asymptote. So how do we find it? Well, we got to go back to your favorite skill of long division, polynomial division. Okay, so we need to find the remainder in order to find the oblique asymptote. Okay, so x squared plus 4, so 0x, sorry, gotta have your placeholder, plus 4 divided by x plus 1. Okay, so remember you have to do your x squared divided by x, which is just x, so you put that above there. So x times x plus 1 is x squared plus 1x. And now I subtract. Remember, you subtract. So you get 0, and then 1. So you get negative x. And then you bring down the plus 4. So negative x divided by x is negative 1. Minus 1 times that is minus x minus 1. You subtract, so I get a positive 5 as my remainder. Now, you're about to find out why I was so picky about how you wrote these statements. So that means that x squared plus 4 is equal to x plus 1 times x minus 1 plus 5. So that means that x squared plus 4 divided by x plus 1 is equal to x minus 1 plus 5 divided by x plus 1. So here we go. Here is the big part where I explain to you why this is the oblique asymptote. Okay, notice this is our function. Okay, that's the function that we're graphing. So we're going to learn how to graph that. It's pretty cool. Now, asymptotes exist when you can't put in no matter what x value you put in, you cannot get a certain result. So this part here can never equal 0. Okay, so because this can never equal 0, that means for this whole thing, you will never have x minus 1 plus 0. So therefore, y cannot equal x minus 1. Okay, so this here on the right side is just another way of writing what's on the left side. And because this can never equal 0, because no matter what you do here, you can't get 0 out of it, this entire right side will never equal x minus 1, because this will never equal 0. So you'll always have x minus something close to 1, but you'll never have exactly x minus 1. So that means that y cannot equal x minus 1, and that is the oblique asymptote. So therefore, the oblique asymptote is y equals x minus 1. Okay? So whatever you have when you do polynomial division, whatever the result is, up here, the quotient, that will be the oblique asymptote. Okay, so if you just understand this part, okay, then you'll get the knowledge part down. This describes why it's the oblique asymptote. All right, so how would we draw this function? Well, we have a vertical asymptote at -1. Okay, and we have an oblique asymptote at x -1. So there's -1. So, you know, you have a slope of 1. So it looks something like this. You could do a bit more exact on your graph. Okay. What else do we know? You could do other things like find the y-intercept. The y-intercept is going to be, sorry, I'm getting a little bit messy here. That's what I'm trying to figure out. So the y-intercept is f at 0, which was going to be 4. Yeah. So that's here-ish. And so from here, it has to go down and approach this asymptote, okay, and go like that. And here, it's going to be between here, and so it's going to go down like that. Okay, we'll go over in more detail in another note about how to actually graph these. Okay, if we go over to GeoGebra, I can graph it, and you can see what it looks like. Okay, so f at x, or I'll call it g at x. G at x equals bracket x squared plus 4. Okay, I have to put it in brackets, so when you divide it by, that all stays in the numerator, x plus 1. Okay, so you can see if we zoom out here, they don't graph the asymptotes, but you can see where the asymptote is, okay? So that there's an asymptote here at x equals -1, and a slant asymptote there. So you can play around with that. You can go to GeoGebra and zoom even further out and kind of see what that looks like. That's what it looks like there. All right, back to the note. So now that we know how to find an oblique asymptote, we have 2 more examples on the last page where we need to find all the discontinuities. So remember, we always look for all 4, even though we know that at most there can only be 3, because you can never have an oblique and a horizontal asymptote on the same function. So first thing we want to do is factor this guy. So you get x minus 3 over x plus 4, x minus 3. Okay, so right away I notice that I have a hole at x equals 3, because these cross off and give me the function 1 over x plus 4. So really my function is just going to look like 1 over x plus 4 with a hole at x equals 3. And actually that would give me 3, and the y value would be 7, I know, from putting 3 into this function. Now I'm going to have a vertical asymptote at x equals -4, because that makes the denominator 0, but not the numerator. Okay, now I have to decide, is there an oblique asymptote or a horizontal asymptote, or neither? Well, this is a bottom-heavy function, which means that I'll have a horizontal asymptote at y equals 0. Okay, so therefore there's no oblique asymptote. It's not top-heavy by 1. Okay, the domain then is x such that x cannot equal -4 or 3, but it could be anything else. Uh-oh, there's the bell, better hurry up. And the range is y such that y cannot equal 0. Okay, remember that you actually have to make sure that y can't equal 0. So set your function equal to 0 and you'll see that it won't work. Okay, don't forget to check though to make sure that you have to exclude the horizontal asymptote. Okay, so over here, you'll notice already that I'm going to have an oblique asymptote because it's top heavy by 1. Okay, so first I'm going to factor, so I get x plus 3, x minus 2 on the top, and x plus 2 on the bottom. So there's no holes because nothing crosses off. I have a vertical asymptote at x equals -2. There's no hole. and there's no horizontal asymptote since it's top heavy. But I do have an oblique asymptote, so I got to do this division. So x squared plus x minus 6 divided by x plus 2. Okay, so x squared divided by x is x. Multiply down. When I subtract, I get negative x, so I get minus 1. I bring down the minus 4. Minus 1 minus x minus 2, so then I get a remainder. I know you can't see because it's behind my head. I get a remainder of 2. All right, sorry, of negative 4, because this should be a negative 6. There we go. Remainder of negative 4. Yeah. I'll find you. I'll find you. I'm just recording. I'll bring it in like 1 minute. Okay. Okay. So therefore, this is your oblique asymptote. Y equals x minus 1. Okay. So then your domain is x such that x cannot equal negative 2. Okay, but x is in the set of all real numbers. And your range is any real number. All right, class is starting. I gotta go. Thanks for watching. Hope you learned lots.